Okay, in this video I'm going to continue on with exercise 5A of the book Fundamental Applied Mathematics. We're on page 119 and the question is 12. It reads, a golf ball of mass 1/7 kilogram falls vertically and lands at a speed of 1.4 meters per second on a marsh. If the resistance to the marsh to the motion is of magnitude 2.1 newtons throughout, find the depth to which the ball will penetrate the marsh before coming to rest. So we need to draw a free body diagram of the motion. So let this be the ground, and I'm going to draw the gravity vector, of course, because we are on Earth. So I'm going to say the gravity vector is negative 9.81 j hat. Alright? So the next thing I'm going to do is draw the velocity vector. So we're told that the ball hits the ground at 1.4 meters per second. So it's going to go in a negative j direction, so the velocity of the ball is negative 1.4 in the j hat direction. We're told that the resistance to motion is 2.1 newtons, so that's going to be in the positive j direction. So the r vector is equal to 2.1 j hat. Now, is there anything else? And the answer is that there isn't. So we need to work out, first of all the forces involved. We have the force being applied by the marsh on the ball, but we don't have the force being applied by the ball on the Earth. Alright, so because we only have a velocity vector. So we need to get this into a force vector. So we know, of course, that the sum of the forces through Newton's second law, the sum of the forces is equal to the mass times the acceleration. So that means the sum of the forces on the ball, this is very important, is equal to the mass of the ball times, that's not a vector, times the acceleration of the ball. Alright, so this turns out, of course, as you well know, to be the weight. So we're going to get the mass, which is a seventh, times its acceleration, which is g. That's going to be equal to the force of the ball. Alright, the sum of the forces on the ball, and that's going to be equal to the weight vector. So it's going to be equal to g over 7 j hat. Now, of course, this is a negative number because g is a negative number. So we know that the weight vector here, the weight vector is equal to g over 7 j hat. Alright, so now the question is, have we got all the forces? And I'm going to say to you that we do have all the forces. So once again, we need to apply Newton's second law, that the sum of the forces is equal to the mass times the acceleration. And this time we're talking about all the forces. And so this is when the ball actually hits the ground. So initially when we were talking about the weight vector, we're talking about when the ball is just in the air. So now we're talking about the mass of the ball and the acceleration of the ball when it hits the ground. Of course, when it hits the ground, well, then there are going to be additional forces because the ground is going to respond. So we're going to get the following: the sum of the forces is equal to g over 7 j hat plus 2.1 j hat is equal to 1 over 7 times a is equal to a over 7. So if you plug this into your calculator, you're going to find that it's 0.7 j hat is equal to a over 7, and therefore a is equal to 4.9 j hat meters per second squared. Now what you need to do here, of course, is ask yourself, is this physically possible? Does it make sense? So what direction is this? Well, this is an acceleration of this direction. And does that make sense? Well, the answer is yes, and I'll tell you why. So if something is falling, right, it is being accelerated, yes, by gravity towards the Earth, but if there was no other acceleration, it would fall to the Earth. But watch my marker. My marker didn't fall to the Earth, it stopped. So there must have been a force and therefore an acceleration, because we know from Newton's first that if there is a force E, there must be an acceleration, and if there is no force, there must be no acceleration. But in this case, my marker is being stopped by the Earth, so therefore there is a force, and therefore there must be an acceleration. And in order for it to stop it, currently my bar is moving in a downward direction. In order to stop it, the force and the acceleration must be moving out of the page towards your screen. So we have an acceleration vector, which I'm going to draw in green, my acceleration vector is going in a j-hat direction, which is exactly what we're saying. So that does make sense. You need to stop, that's how you stop the direction which is required in order to stop the marker, or in this case, the ball. So what were we asked to find? We're asked to find how far it will penetrate before it will come to rest. So this is just a small application of accelerated linear motion. So we apply our UVAST. So we know the initial speed is negative 1.4. Now of course directions here are vital, okay? So we're going in a downward direction here, or yeah, we're going in a downward direction with our initial velocity. We're going in an upward direction with our acceleration, which is 4.9. The final velocity, it has to come to rest. So let's apply v squared is equal to u squared plus 2as. Alright, and we're going to get the following. 0 squared is equal to negative 1.4 to be squared plus 2 times 4.9 times s. Therefore we're going to get negative 1.4 to be squared divided by 2 times 4.9 is equal to s. So it's looking like we're going to get a negative distance, or a negative displacement, excuse me. So it's going to be 1.4 to be squared divided by 2 divided by 4.9. We get a fifth, so we're going to get s is equal to negative 0.2 meters. That is our displacement vector, and it's going to be in the j-hat direction. Alright, because these vectors are all in the j-hat. I could easily just write that like so. Alright, so does that make sense? You need to ask yourself this the whole time. And of course it makes sense, because it's going into the ground, so the ball is landing, say, somewhere here. And the marsh, as we know, is compressible. So it's unlike my table. When my marker hits the table, to our eyes it doesn't compress, which is fine. It compresses somewhat, but we can't see it. But a marsh would definitely compress, and it compresses by 20 centimeters. And we know it compresses because it's a negative displacement. If it was a positive displacement, then somehow if the ball hit it, it would get the marsh to lift up. But we know that doesn't happen. So thanks for watching. Please pass it on to your friends and subscribe to my channel.